looking at another example here, but we've used trigonometry in a right triangle before, right? In a lecture before, and we turn our attention over to inverse function. And so, just like that, right? When you're on a right triangle, say an angle theta here, then we've got opposites, right? Relative to that angle, and then you've got adjacent, and then you've got hypotenuse, right? And so, again, we call for the sine of theta. If we're looking at that theta over here, the sine is opposites equal to opposites, like divided by hypotenuse, right? That's why there's a so, and then cosine of theta. That's just a brief reminder. It can be equal to that ratio of adjacent over the hypotenuse. Okay, so all of these is coming back, right? And then tangent, at least, we can define tangent to be opposite over hypotenuse. We have proven that tangent also equal to that ratio. So now we're gonna, with our understanding of the inverse function, we're enabled to do some more problems, even more problems on the right triangle over here. So now I'm gonna bring in a picture. So we just basically want to find the unknowns. Okay? All right. So that's the example, and then to continue from last example in the same lecture here, let's just call it example 4 here. But this is where one place we can see the usefulness of the inverse trig function. So let's say I can, and really the order of these shouldn't matter, whichever among the three unknowns here we want to find out first. That's completely under our choice there, right? So how about that remaining lecture here? Like I said, it's just my choice there. But when you guys are working with a problem similar to that, then you have your own choice of finding out whichever unknown that comes first. So a over here as a length, right? We know that a squared, Pythagorean theorem, a squared plus 5 squared, right? The other leg is going to be equal to the square of the hypotenuse. And so in that way, right here, clearly, and 5 squared is 25, 12 squared is 144, right? So clearly we can go a squared equals, right? And I'm going to subtract the 25. Let me note that with red ink here. So we subtract the 25 from both sides of the equation, right? Because that's 5 squared right there. And so we're going to end up with so a squared will come out here 144 minus 25 there, right? So a squared equals that's going to make it 119 there. So now a itself, and these are all positive lengths. So now we're going to take the square root of both sides, right? So technically taking the square root, or algebraically taking anytime taking the square root of both sides of the equation, we end up with plus or minus 119. And once you guys really nail down with that routine, and then we make our choice. So our choice here got to be the positive one, because a has to be a positive length, right? So we go with positive choice right here. Square root of 119. We have found one of the unknown. And for simplicity, let's keep those in exact value that way. We don't want to go with decimals here, right? Now we fill it in, we found out that this length right here now has been found to be, right, so that equals square root of 119. Right? So I'm going to keep going back to the picture itself and make notes there, but whichever the information we found from being unknown, I'm going to label that when we're ready. So now we got the two angles that remain. And so this is a skill that we weren't able to do that before when we were looking at when we were in that lecture learning specifically about trigonometry and triangles. But now with our understanding of the inverse function, we should be able to handle. So how about I'll work with B first, okay? So B as an angle, the measurement for B as an angle. So B is here, the opposite of B is 5, right? And then the hypotenuse here is 12. So I can see opposite, and I'm using directly the information that was already available. It's not even, I'm not even using that other one that we just found, and that's really your choice like that. So I'll go sine of the angle B like that, right? Has to equal, so remember, opposite over hypotenuse. So from where B is, 5 is the opposite. we got 5 over 12. So we got a ratio, right? So we know sine value of B, of that angle B has to be 5 out of 12. So now can we go from here to find out how large B is? So now B has to be what? And that's the whole reason of learning about the inverse functions, right? We've added that kind of problem right here that we want to find out what angle having sine value equals this. And so that means now applying our understanding that we're looking at taking sine inverse, right? Our function here is sine of B, so we take sine inverse of this given ratio as positive by 12. Now that calculation is ready for us. And so as said earlier, let's keep all angles in degrees here. Okay. And so in that way, you guys go ahead and we can go ahead and run the inverse trig calculation with that, or on 512, and go ahead and get me an answer. All right, so I can hear from your calculation, 24.62. Thank you. Okay. Right. Now the two decimal places, decently good. So we found one angle. So I'm going to go back into this picture right here and label. So D now has to be about 24.62. So now we have that tool to handle. We're allowed to do more work on the right triangle. And so we've got one remaining unknown, right? The angle A. So right here from where A stands, right? You can use that 5 right here as it's the adjacent, right? And then adjacent relates to cosine, right? So adjacent over hypotenuse, that's cosine. And now I'm going to say cosine of the angle A right there. Has to equal 5 over 12. And then that means once again we have that. We want to find out A here as the unknown, and A is equating the role of an angle. And so what we have here is a trig equation, right? So solving this trig equation, that means we are applying our cosine inverse operation. So cosine inverse of 5 over 12. Okay. That's the way for us to get to that, how big that measurement of the angle A is. Okay. So go ahead and get me that value right there. Cosine inverse of 512. Alright, so the calculation came out 65.38 degrees, okay. Right. 65.38. 65.38. And so let me open up another channel working with this problem again for you guys. So that's one way of how we find A, right? But when it comes to this remaining angle, I'm talking about in a situation here where we've got two unknown angles, right? And we have found one using inverse trig function to get that. We can find the other angle by using the inverse trig function as well, right? That's one option. But then for this remaining right here, think about it. I mentioned earlier, the A and the B are playing the role of those two acute angles in our right triangle, right? And so they always have to add up to be what? 90 degrees. Right? And so you didn't even have to go that complicated work, because I just want you guys to get comfortable with, to provide more opportunities for you guys to use the inverse trig function. But in reality, you didn't even need to go here, right? You can just easily go. The angle A can just come out being what? 90 degrees. Subtract away the previously found measurement for B. That's 24.62 degrees, and the answer would come out exactly that. Okay, 65.38. So sometimes due to the rounding, we may be slightly off, right? But it shouldn't be too much of a big difference. Okay, it won't be too much of a difference. But then in the end, we've got a couple of different channels how we can handle that same problem. Right? So again, with our understanding of inverse trig function, we should be able to bring that back into solving a right triangle problem again, right? And so we've been calling these inverse trig functions, but in the end, I haven't really defined any trig function, any inverse trig functions yet. So at this point right here, you see, by far at this point, I want you guys to realize I've been introducing, in my style at least, I've been introducing inverse sine or inverse cosine, right, of a value, whatever k that is, or a value whatever k that is, right? Or inverse tangent, or inverse secant, inverse cosecant, whatsoever. I've been referring to these more as an operation. You know what I'm saying? That's something that we do to a given value, right? But in the end, the final truth comes out is that we can really define, hey, sine inverse. We can define that as a function right here. We can define a function f of x to be the sine inverse x, because the nature I can see here is that we can apply the same operation here on various different inputs, right? As long as our inputs for sine inverse here, as long as the input stays anywhere from -1 to 1. So we've seen all of that detailed here. And so now we can just simply define, right? We can define a function. Right? We can define that f of x being sine inverse of x. So this is now, right, as a function. Right, so that's, we got the sine inverse function, and then we can purposely define it. Right? In other work, then we can also define a function f of x, right, to be cosine of x, cosine inverse of x. Yeah. As a function as well. Okay, so we can define a function f of x to be any one of these. Okay, so these are different definitions of a function. Yeah. And then keep in mind that the x here can only, our inputs for an inverse cosine only happens anywhere from -1 to 1. So I wrote down two functions here. I'm talking about it's not the same thing, two different things right there. So if you define your function f of x as a sine inverse function, then here's the thing. You see there was a restriction about the x that I explained before, right? The x, this sine inverse can only take values anywhere from -1 to 1. And so now when we're formulating that as a concept of function, then the domain of this function here, we are pre-calculus people, we gotta start getting comfortable with understanding the domain of any function, right? Because when you guys later on go to your higher courses, yeah, the idea of domain is very important. So the domain for this function, the possible input values that this function can only take, those are just in interval notation, -1 to 1, right? Because this function, sine inverse of x, in the way how we understand about the sine inverse operation, it only takes inputs anywhere from -1 to 1. So sine inverse has that domain being -1 to 1. And we just formulating all of those ideas we have seen, and then put that into the functional concepts. And so the range, which is the set of outputs that the function can give, right? So sine of x, we're looking at sine of x here as our function. Then recall that, hey, when you're, again, taking sine inverse in the purpose of coming out with an angle, right? This is, the x here is a sine value. So we're taking the sine inverse. The output here has to be an angle. So I've been saying that quite a few times up to this point. The outputs, the angle that comes out from sine inverse, there's a restriction. We only go from -π/2 to π/2. So that's going to be our range for this. Later on, I should be able to, once I put in the graph, I should be able to explain why people have chosen the range for the sine inverse to be from -π/2 to pi, to positive π/2. Right now, we just take that as something that chosen, right, by mathematicians before us. Okay, but there's a reason for that. We'll get into that. Okay, so that's something to know about the domain and range if our function is defined as a sine inverse function. So in that same way right here, see? Now if we define a function f of x as a cosine inverse, right? Remember that restriction right there. This cosine inverse operation, first thing in line, it can only take values anywhere from -1 to 1. And so that becomes now immediately our domain. If we define cosine inverse as a function, then we've got domain here being that interval from -1 to 1. Those are the x values you get, right? That's a closed interval. And then cosine inverse got the similar, actually cosine inverse has a different range here. The range for cosine inverse goes anywhere from 0 to pi. Remember the angle that comes out, the angle that's generated by taking the cosine inverse comes out being anywhere in the upper half of the unit circle. Okay. The idea is like this. And we only take that upper half. That's why. Right? 0, 0, pi is here. So taking cosine inverse, see any of the cosine value right there? Right? When we take the cosine inverse, we only want to land into an angle that's angle that in the upper half, so 0 to pi. We got the domain and range for our cosine inverse function. And then tangent can also be defined as an inverse trig function. And so the same with the other, like the secant inverse and the cosecant inverse and the cotangent inverse. We can all define a function based on those as well. But let's just mostly focus on the sine inverse, the cosine inverse, and the tangent inverse. Now we can define another function f of x, right? A different function f of x here, even though I use the same name. Tangent inverse of x. Right. Now, tangent inverse doesn't really have the x value right here does not really have a restriction for that. Tangent inverse can take any x values, right? Even 0 or any positive value or any negative values. But then, so in that way right here, yes, we can define that as a function, right? Then in that case, the domain, in what I was saying earlier, the domain for tangent inverse now is going to be anywhere from infinity, negative infinity, to infinity, anywhere between those. The whole line of real value there. But then also, I have mentioned before that when we take tangent inverse of a tangent value, right, we should come out as a restriction again. We should only come out with angle if it was decided as a convention. That we only come out with angle anywhere between, and strictly, I'm talking about strictly anywhere between minus pi over 2 and pi over 2. Right, so now it's only a closed, it's only an open interval, not even including those 2 points. So we won't have angle that falls precisely negative pi over 2 or pi over 2. We won't come out with those angles. Okay, so I want you guys to look at this one more time. Okay? I'll try to explain the reason why the range for the sine inverse function, why mathematicians before us have chosen the range to be minus pi over 2, pi over 2. Okay? We're going to find out why here. Right? Because that has been introduced since the beginning days, right? When we only come out with angle theta, when we take sine inverse, we only come out with angle theta being from anywhere from minus pi over 2 to pi over 2. And now we're going to get really into that reasons like that. Right? So let me now remind you. Now from calculus, from pre-calculus 1 that we have learned, this is the graph of sine of x here. Does everybody agree? We've seen that all of that, right? So from our understanding, having an inverse function, a function like this fails to be a one-to-one function because think about a horizontal line right here. Y equals a 1/2, for example. There's a horizontal line that crosses this graph at so many points. So this function, in other words, sine function fails to be a one-to-one function. The sine function is not a one-to-one function. So technically speaking, according to what we've learned from pre-calculus 1, then sine function does not even have an inverse. See what I'm saying? No, but now we do want to define a sine inverse. So we are forced to do the following. So before we can get the actual sine inverse function, we're gonna have to restrict. So now if you're looking up to the left of my screen right here, see, instead of taking the full complete, right? Instead of taking the full complete graph that's waving up and down and all over the line of real numbers here, I'm only gonna restrict that. It's just a choice that we're gonna restrict it between minus pi over 2 and pi over 2. So this is, I'm talking about the starting angle, the starting sine function. We only restrict the domain of sine angle, of sine of x to anywhere from minus pi over 2 to pi over 2. Let me change this a little bit right here. Alright, so we got the graph, the portion of the sine of x graph, just only happening from minus pi over 2 to pi over 2. You guys see what I'm doing there? And now let me show you the graph for sine inverse here. And sine inverse also has another name. Like instead of writing the superscript -1, you can also write arc sine of that. That's another name for sine inverse. Okay, now I click on the graph. Now that graph is right here. The graph in blue. Okay, so let me bring that here so everyone can see it clearly. Okay. So that graph right here in blue is sine inverse. Right. Let me name that y equals sine inverse. And so let me hide away the red sine. So the picture of the sine inverse looks like that. Now clearly it a value here being, see, I just now popping that point right there, right? You can see that right there, it's -1. And I couldn't hold it right there for too long. But see, that's left point that my mouse cursor is pointing at. That's right. It's -1, and the low it hits was a -pi/2. Like and then the high, according to the right hand right there, right, it reached a high right there being a +1. So that's consistent with the domain of our inverse trig function had to happen anywhere just from -1 to 1. We all look at that somewhere, right? But here's the thing. If we recall from math, from your pre-calculus 1 course here, let me put in this line, right, the black line here, the black 45-degree lines, right, and then let me put that dotted. You see, graphically speaking, the way how it is inverse function and the original function are always supposed to be mirror reflection through the 45-degree lines. So this line, this dotted line I just put there, is a 45-degree line. And so that's why the blue, that which is the graph for sine inverse, is the exact mirror image, right? The blue is the exact mirror image of the graph, right? Through the 45-degree line. And that's the reason why people chose only, so think about the complete sine, right? The complete sine function is here, right? The complete sine function is running on forever, right? It runs on forever right there, but then we purposely only choose the part where we can only choose the part from -pi/2 to pi/2. That's the reason why we choose, so that we can, when we take the mirror image, right, we have an existing mirror image through the 45-degree lines. See what I mean? Okay. And so from now on, when you think about the graph of the sine inverse, right, we don't have to do too much transformation with the graph of the inverse trig function. But now the graph of inverse sine, you see on the board I write sine with a superscript. Computers a lot of time write arc sine like that. Same notation, same meaning, right, with different notation like that. So the picture is like this. When you get the graph of arc sine or the graph of sine inverse, see, there's -1, there's a 1, that, right? And then it goes right through the origin right here. So pick the scale, we could call the bottom here as a -pi/2. And the top here, the same distance here, you call that a +pi/2. See what I mean? So it goes like this, one way up, right? But it's one way up, but don't go straight up like that. It goes like this. Bend shape, right? Like that. That's simply it. Your sine inverse of n. One easy fundamental picture like that. See what I mean? So that is the reason why, back on this thing where we concluded our explanation. That's the reason why we chose the range here, right? We explained that graphically with that. Okay. So now again, as I did earlier on the board that you have seen it, right? If we define the function f of x to be the cosine inverse of x, the domain is, as usual, it's a cosine value, so it makes sense that cosine value only happen anywhere from -1 to 1. So we got out of that explanation. There's no need to require. But why has it always been that the range, the angle that comes out from cosine inverse can only be anywhere from 0 to pi? So it's a choice that mathematicians before us chose for us. But now we want to see why. I'm going to put a question mark there. So let's give some reasoning through the graph right here. So the domain information is telling us that arc cosine takes the domain from -1 to 1. So that information. And so along with that way, now I can see that our graph right here, the domain happens anywhere from, once again, the left point, or the far left point here was a -1, right? And it gives the high point being pi. And then the ending point right there, 1. Okay. So the domain is consistent with what we have already drawn down, right? But why has it been chosen like that? Why has it been done like that? So remember now, this line, this graph in blue is supposedly the mirror reflection of the cosine graph. Okay. So I'm going to put in cosine of x graph here. but through the mirror reflection through that 45-degree line here. So cosine is right here. See that now? Okay. That's the cosine. Right. Let me move it out of the viewing area so everyone can see. Right. So the cosine is the complete waving ground one right here that goes up and down, up and down. But then cosine itself, again, fails to be a one-to-one function, right? It's one horizontal line can cross this graph at so many points, at multiple points. So cosine itself does not qualify to have an inverse, does not qualify to have a cosine inverse. And so for that reason, we're going to restrict. Okay? So we're going to restrict that. Here, we purposely choose, we want to restrict that in a way that it's consistent with this blue graph here. So we restrict that between 0 and pi. So now, after that restriction, I'm going to show only the restriction part of that. Okay, so now with the customized picture of that. So cosine, now this is our cosine. It's only a cosine that's under the restriction that it goes from 0 to pi. Right? So now for the cosine, if we restrict the angle from 0 to pi, and so that domain of our original function becomes the range, right, of our inverse function. Right? So that's how it happens. Yeah. So now back on that board, you can see that we define a function y equals cosine inverse of x, right? Or we can write that using the other notation, arc cosine. Arc cosine of x. Same way. Yeah. But in that way, our function goes like this. -1, 1, right? For our arc cosine would be -1 is going to give us a high point, and that's about a value that we call pi. Right? So the scale of we call it pi. It hits down to 0, so it goes the range goes from 0 to pi, right? 0 to pi. So it goes like this. It crosses through right at about pi over 2. A little off there. Right? That's how it happens. So the last information. So we wrote on that definition earlier, right? Now when we define that function to be the arctangent or tangent inverse x, the domain we have agreed previously that it goes anywhere. I mean the domain is anywhere on the real line, between minus infinity and infinity. But then the range for this function, taking tangent inverse only comes out with angles anywhere between minus pi over 2, pi over 2. Okay. And that's once again, let's go into the explanation of why it's taking that range there. Right? So the graph for arctangent is like this. So apparently the graph so agrees with the domain. It runs anywhere from negative infinity to infinity. So we have no problem with that at all. Okay. All right. So once again, this is our tangent inverse. So it agrees with all of the domain right here. I can just keep zooming out, and you see no matter how far we go on the x-axis, there's still tangent inverse existing there, right? So the domain is anywhere between minus infinity to infinity. But now, think about it. This blue line right here, think about it. This blue curve would be the mirror image of some other graphs through this 45-degree lines. And let me now show the tangent graph here. See, tangent graph looks like that. It's all over. And so the problem now is that, see, tangent graph, tangent, sine, and cosine are all periodic, and that's why they for sure fail the horizontal line test to be the one-to-one function. And so now, among all of these pieces right here, see which one is a piece that seems to be the mirror image of the mirror image through the 45 line right here, 45-degree line of that blue one. If this portion right here, right, this portion is the only one that being the 45-degree mirror image. And so in that way, we have to restrict our tangent. Right? So for our tangent, here, right, I'm going to restrict that down to only that interval. Right? Oh, only in that interval anywhere between minus pi over 2 and pi over 2. And now we have mirror image between the mirror image through the 45-degree lines, right? Between the blue and the red. Right, you know that field, right? And so now tangent inverse itself right here, you pay a little closer attention. Pay your attention a little more closely right here. It's indeed asymptotic to a certain line of them. So let me put in that line. How about y equals pi over 2. Let me put that in black ink again. Dotted line. Then pi over later. Extra one. Yeah. And let me put down minus pi over 2. Okay. Put that in black color. So it turns out, based on our observation, that tangent inverse function is asymptotic. Asymptotic to these two lines here. See, pi over 2 and negative pi over 2. Those two values together. So our tangent inverse function happens strictly between those. Okay. And so from this point on right here, think about any time that tangent inverse is mentioned to is brought to your attention, right? Any time that the tangent inverse function is brought to your attention, and think about the graph being like this. There's a one way going up, right? Rising from the left to the right. There's a line upside, we call that pi over 2 again. There's a line at the downside, right? Restricting the graph, we call it minus pi over 2. Easy enough to understand? And then it goes asymptotic, so make sure it's not going to cross. That's the idea of asymptotic, right? It's horizontally asymptotic, so it's going to go like this. And it crosses right through the origin, going up like that. We're not artists here, so we're not expected to get the exact and the best looking picture of tangent inverse, but that's what it looks like. Okay, see, it's one way rising, right? It crosses right through that origin, and then be asymptotic to both lines up and down. So you see with the graph for tangent inverse. See what I mean? Right? And so in that way, after concluding a few things in here, my board is getting narrow here, but allow me to put in some extra understanding. Okay. So remember the odd and even symmetry that we discussed earlier. So negative 1, 1, there's pi over 2, and minus pi over 2, right? The graph for sine goes this. Okay, remember that? Okay. And so y equals sine inverse. Graph for sine inverse. That's what it is. Okay, so now you can see that sine inverse here has asymmetry. So think about that point right here. 1 comma pi over 2. Right? It has the exact mirror image through the origin, right? Right to the other points, right down here, being negative 1 comma negative pi over 2. See what I mean? And then every point on one side of the graph, every point on one piece of the graph has an exact mirror image, right, through the origins on the other piece. See what I mean? And that's why sine inverse here is odd, right? Now, because once we are defining it as a function, the sine inverse of x is odd. And being odd further means if you take the negative inputs, right, it comes out being minus of the sine inverse of the usual ordinary inputs x. That's fundamental relationship anytime that you're looking at it. Odd symmetry. Cosine is indeed, odd cosine or cosine inverse is indeed neither. It's neither the odd or even. It's just some function out there. But tangent inverse is also odd. Right? You pick a point here, right? There's a point, you can find the exact mirror image on the other side. pick a point, right? We can find the exact mirror image on the other feature. Yeah. So now including it as a bottom line tangent inverse is odd. Odd function. And then fundamentally that means tangent inverse. When you taking the negative input, right? It's the same as taking the positive input of a tangent inverse, but the answer comes out being negative. Right? So those are the properties with the three fundamental inverse trig functions. And then for the other inverse trig function, like the inverse cotangent, inverse secant, and inverse cosecant, any one of us here can just read through any textbooks or web resources to find out how to graph and all that. Those are usually not too focused. Okay, we don't have to focus on those, but these are at least the important ones. Right. Any questions for me, please, ladies and gentlemen?